The very first thing is, so what is the impact of adding or deleting terms from a series, so we can always add or delete finitely many terms without altering the series, convergence or divergence. That means it may not, it will not have any impact on this. Okay. So second point I want to make is, if something is convergent, then of course, if you subtract few terms, even then it would be convergent, right? So let's say mathematically, I would write it as, if this is convergent, then if your summation an is convergent, right, then
Yes, sir.
it doesn't matter if you start from, say, let's say k, and you left k minus 1 terms, it will still remain a convergent series. Okay, that's what I pointed out, right?
Yes, sir.
Okay, so let me finish with these words. So let's take an example in order to understand this. So let me clear this page. Now I'll rewrite the example again. So example is, if you take this series, right? So you know that this series is can be expanded in this way. Okay. Anybody, can you tell me the sum? What would be the sum?
Sir, 2. 2 will be the sum.
A upon 1 minus r. So it is 1 upon 1 minus half. Right. 1 upon 1 minus half. So that is 2. But if you start from, let's say 2. Okay. So 2 to infinity. So what will happen? What do you think?
Only the sum will change.
Yes, convergence will not change. So we'll actually leave these two terms. Okay, so that means if we see the sum of this sum will become 2 minus these two terms will be removed,
Half.
1 and minus half. So sum will remain only
Half.
half. So sum will change only. Okay. Otherwise, if it is convergent, then of course it will become convergent, and if it is divergent, it will remain divergent. Okay. So there is no such changes. Now next thing is, can we make that is something which we call it as reindexing. Okay, so reindexing will not change the convergence, divergence, even or like the sum. The only thing is sometimes the changes in the in say, let's say, in the index will help us a lot. Okay, so I'll not go to the particular examples of this, but I only tell you that what is the reindexing. So reindexing, can you see this series?
Yes, sir.
Can you see this?
Yes, sir.
Right.
Yes, sir.
So if I want to write it, let's say I want to start it from 5, but I want to keep the expansion same, but here I want to start it from 5. I want to write it in terms of 5. What should I do? So I'll make a back shift over there, right? So understand. So here the series is this. Okay.
Yes,
So
sir.
you want to keep the same series. You want 1 by 2 0, 1 by 2 1, 1 by 2 raised to power 2, and so on up to infinity. So if you want that there should be 0, just like this series, but here it is n minus 5. So what value of n is suitable over here to make it 0?
5.
Of course 5. So you should start it from 5, right? So this is what it's a kind of back shifting. What do we call it as a? We call it as a back shifting. Okay. Now we have another ways to do it. Now let's say we have a series. Now what is that? Okay. Now suppose you want to write it start from 0. You want that it should start from 0, but it should have the same thing over here. Okay, so let me make it more clear. Okay, so here you want to start it from 0. So from 0, that means you will add something here over. What? That is what? 2. Okay, so we'll keep it 2 over here, and then Q, then everything is fine. Okay, so you may have a backward shifting, you may have a forward shifting. This is kind of backward shifting. This is a backward shifting. Why? Because we want to start it from the summation from n is equal to 5, but we want the series to be start from 0. So that's why we need to give a back shift of 5 over here. And similarly, in the next example, we have 2 over here, and we want it to be start from 0. So of course we need to give some push over here, and that push is exactly equal to this. That means 2. So it is not like that you always start from 0 or always start from 2. So it may be like that you want to start it from 1, right? So that 1 is already there. Okay, so that 2 is already there. So what kind of shift it can have now?
n+1.
Yes. Right, because we want to start from 1. That's it. So you calculate the shift from this and this and this together. You need to see to the 3 things that from where you want to start the index and from where you want to start the series. So that's how you adjust the things. Okay.
सर
Yeah.
सर अगर इससे हमारी सीरीज पे कोई फर्क नहीं पड़ा तो ये करने का फायदा क्या हुआ?
मैंने यही बोला तुम्हें कि we need to make some adjustment accordingly. ठीक है, कई बार हमें कुछ टर्म्स बाहर निकालनी पड़ जाती हैं. Let's say I'll give you a very rough, very simple example. Okay, let's say I have 2 things. One thing is here and another thing is, let's say, here. Okay, now can I write in this way? 1.5 plus, can I write in this way?
Yes, sir.
Yes, sir.
This is the example of the first thing, that we can add or delete finitely many terms. Okay, so this is the benefit, that now you can keep it in the same summation. Okay, so how are you gonna write it? You're gonna write it as 1/5 plus. So this is now your summations are same in the nature. Now you can write it in the same expression. Okay, so things become little compact. Now let's say you have an example. Let's say case 2. You have an example that you want to read reindexing. Now where the reindexing will come into the picture? Now let's say you have n is equal to 2 to infinity 1/5n, and let's say you have n is equal to 0 to infinity 1/2n. So what are you gonna do? You want to start it from 0. Okay, let's say you want to start it from 0. What are you gonna do? N minus 2?
Yes, sir.
Sorry.
n+2.
N plus 2.
n plus 2.
Right? Now your summations are aligned. They have the same starting and same ending.
Yes, sir.
Okay, so now you can write it in another way as summation n runs from 0 to infinity 1/5n plus 2 plus 1/2n. So that's how you can keep the things in the same bracket with one summation. Okay, so in these types of calculation, you generally write just to make the things compact, or just to align few summations to align few series in one summation. Now I'll pick 2-3 questions from this exercise as well, which we have left. Okay. That is, let's say question number 72. Now it's very easy. It's very easy in 8.3 exercise. It's very easy, but sometimes you read the statement, you feel like, I don't know, what is this? You know, something like that. You feel it like pretty much complex. So show that the error L minus Sn obtained by replacing a series, a convergent geometric series. Let me write it more precisely. Convergent geometric series with one of its partial sums Sn is this. Okay, कुछ समझ में आया स्टेटमेंट में से? कुछ भी समझ में नहीं आया?
नहीं सर, नहीं आया
सर नहीं
लेकिन ये
है।
बड़ा आसान है, बड़ा आसान है. Let me tell you how it works. Okay, so now you want to, first of all, you keep your eye over there, that you want to find out this thing. Now what is your L? L is the sum. Normally I write it by S, so you can also write it by S minus Sn. Okay, so you want to say that your error term will be equal to this. So can I do this? Let's say how I do it. So since it is given that it's a GP with first term A and let's say common ratio R. Okay, so if you have S infinity, which I call it as S, so that is what A upon 1 minus R. So let's say if I don't take the whole series, I'm not considering the entire series, I just take the first n terms, then it will become this. Is it okay?
Yes sir.
So
Right. So in question, this is called to be L. We generally write it as S. So let's say we call it as L. So if you take L minus Sn, that means your A minus this A1 minus Rn upon 1 minus R. Right? Can we write it this way?
Yes
So
sir.
if you take the LCM A1 minus R, if you take, let me take it to the next page. So 1 minus R is common in the both denominator. We are having the same term. So let's say we write it as, of course, 1 minus R. And this A is common, right? So take this A as common, 1 minus Rn. So it is that. So 1 and 1 will get cancelled. Okay. So we are left with this, right?
Yes sir.
And that's what we wanted to prove. That is here. Okay. अब समझ में आया?
Yes sir.
Yes, sir.
So you have nothing to tell. You just want to tell that कि अगर ये sum इतना है और n terms इतनी लें तो error जो है वो इतना बचेगा. nth stage के लिए error इतना बचेगा. But question number 75. So it is your question number 75. It says that we have a figure. Okay, we have a figure in this way. Okay, so it's a square. Okay, and we make another square into that. So now again you join the midpoint of the internal square and you will get another square. Okay, so you again join the midpoint and that's it. You made another square. Okay, so say that you keep doing this infinitely many times, right? And the next thing it wants to say you that the outermost square has area of 4 meters square. Now, if you keep on adding those, if you keep on constructing new squares, how much area you will get as a sum of the sum of all those the areas of those squares. Okay. Now, I want to tell you one thing here. See, the outermost has a 4 meter square area. That means, of course, the side is 2 meter.
Yes, sir.
Yes, sir.
Yes, sir.
Right.
Sir.
So
Yes.
if your side is
sir.
2 meter, so you know that midpoint will occur at 1 meter.
Yes, sir.
Yes.
Okay. So now this will become a right angle triangle
Yes, sir.
Sir.
because you know that this angle is always 90 degree. Okay. Since this is a square, that's why. So now if it is right angle triangle, so it will become root 2.
Yes, sir.
Sir.
So that means the side of the first internal square would be what? Root 2.
Yes,
Yes,
sir.
sir.
So if we keep on doing like this, if we'll keep on reiterating our argument, so we'll definitely get the square root, right? We'll definitely get the square root each time. Okay. So next thing is what? So I would write it as, so area would be sum of areas. I should write it properly. Sum of areas. First of all, you have 2 square, then you have root 2 square, and then if you calculate the next one, you will have 1 square, and so on like this. Okay, so that means you have a series with like 4, 2, 1, and so on up to infinity. That means you know that your S is going to be A upon 1 minus R. That means 4 times the 2. That means 8 meters square. Question number 31 is from exercise 8.4. Slightly different, however, it's not tough, but it is slightly different. Okay, so we're going to do that part. So let's say how we're going to do it. Okay, so question is n runs from 1 to infinity, a upon n plus 2 minus 1 by n plus 4. We need to decide the convergence or divergence of this on the basis of the values of a. So that means we're going to find that what values of a are good enough to make this series convergent, and on the other hand we want to ask that what are the values of a which will make the series divergent. Okay, so for as a very first step, since this exercise belongs to the integral test part, so we're going to start it with an integral test. We'll try to implement the integral test. We know that the given series is convergent if I take the corresponding series, and if the area under this from 1 to infinity of this function is finite, then I'll say that the corresponding series is also convergent. Okay, are you with me on this?
Yes, sir.
Yes, sir.
Sir.
If this is coming out to be finite, then I'll say that the corresponding series is also convergent. Okay, so let's try to find out the integral. So this is something a log x plus 4, sorry, x plus 2 minus log x plus 4 1 to infinity. So we generally keep a limit t tends to infinity, and let's say this expression can be written as log of x plus 2 power a minus log of x plus 4, and let's say 1 to t, right? That's how we're going to write it.
Yes,
sir.
sir.
Limit t tends to infinity. Since it is log a minus b, so we'll write it as x by 2a upon x plus 4, 1 to t. Okay, so let's say we'll put those limits over there. So that becomes log t plus 2a upon write it properly. Log t plus 2a upon t plus 4 minus log 1 plus 2, 3 raised to power a upon 1 plus 4, 5. Right? Can I write in this way?
Yes, sir.
Now this will become what? T infinity log t plus 2a upon t plus 4 minus log 3a by 5. Now this is something which is independent of t. This quantity is something which is independent of t, right? So it can take any value of a. It doesn't matter. Okay, this will remain always finite. Are you okay with this?
Yes.
Okay.
Yes,
So,
sir.
so we started our claim that if this thing comes out to be finite, then we are okay. Then we'll say that the corresponding series is also convergent. That's how we started. Now we reached over the fact that this is going to be finite. This is always finite. Okay. So we have only a possible problematic figure is this, right? So we're going to deal with only this part now. So we'll say that consider this part only. So consider
Sir,
limit. Yes.
sir, in this A is any positive number?
Yes, A is any number. A is any real number. It
Okay,
doesn't
okay,
matter.
sir. Okay, sir.
So t plus 2 raised to power a upon t plus 4. So I have also, I have also discarded that log part also. Why is it so? Can you tell me?
Continuous function.
Continuously, second thing is what? We are taking t to be infinite. So this is never going to be a negative number. So if it is not negative number, log will not make any problem to it. Right? So this expression will not be a problem to the log. Okay. So we'll be only interested in the internal part. That means this thing. Is it fine? Is it right? Now,
Yes, sir.
Yes,
let's say if
Yes.
let's say if it is convergent. Let's try to move in a direction that it is convergent. If it is convergent, we can easily apply the L'Hopital rule on this. So what we're gonna do? We'll take a plus 2t a minus 1, right? Okay, in this way. Okay, upon 1. If it is convergent, then this will also reach over there. Why? Because this is infinite upon infinite form, right? So now this will be finite only if your a is equal to 1. Okay, the above will be finite only if your a is equal to 1. Because if your a is 1, this thing will become 0, right? So if this thing will become 0, of course, this will be what? Can you tell me? This will be what?
1.
One.
So
Yes.
1.
Yes. So then it is okay. But if this thing is greater than 1, then of course this will infinite and this will be like shooting to the infinite. So to cap it all, I would say that this expression is equal to what? Is equal to infinite if your a is greater than 1 and 1 if your a is less than 1, right? So I would say that our given series, this series, right? We started from this series, which is depending upon this integral. So I would say that this series is convergent for a greater than 1 and divergent, a equal to 1
A equal to.
and divergent for a greater than 1. Now one may ask that what about a less than 1? Okay, so for a less than 1, this is going to be a negative series, and if it is less than 1, we'll not be able to treat the law, right? That it will become a negative harmonic series. If you check this will become a negative harmonic series. That is the part which I'm going to leave as an exercise for you people. So I'll write it over here. For a less than 1, okay, the series will become a negative harmonic series. harmonic series for some m for some m for for all n greater than equal to n. ठीक है, so we'll say that for some m कोई ऐसा m आएगा so that the tail will eventually become the negative. Okay, so harmonic series, therefore it will be divergent. Okay, so let me discuss my last point, which I haven't discussed from the alternating series point. We have done the alternating estimation theorem. Okay, so in that theorem, we said that error cannot be more than the first unused term, right?
Yes, sir.
Okay,
Yes, sir.
so let's we revisit this part. So what did we say? We say that error cannot be more than s minus sn is always less than equal to un plus 1. That's what we said, right?
Yes.
Are you
Yes.
with me on
Yes,
this?
sir.
Yes, sir.
So I'm using one more important addition to this theorem, and that is which I left at that point because I proved only up to this step. So I didn't include that part. So I'm not proving this part, but I'm using this part. So the last part of this theorem was further the remainder or the error. So we may call it as remainder. We may call it as remainder or error. Okay, this is not written well. So further, the remainder or slash error, we generally call it as error, and that is what s minus sn has the same sign as first unused term. So it says that difference of s and sn, if it is positive, then the first unused term is positive, and if it is negative, the first unused term is negative. So let me give you an example. The example is already in the book. You can also check with the exercise as well. So that is what. So let's say you have this thing. Okay, so you know that it is 1 minus half plus 1 by 4 and so on up to infinity. Now it says that you should check it with the first 7 or 8 terms, I guess. Okay, so it says that you truncate the series after 8 terms. Truncate the series after 8 terms. So let's count the terms. So we have first term, this is second, this is third, and this is fourth, fifth, sixth, seventh, eighth, and this is ninth. So we'll keep only these terms into the picture. Okay, so we know that how to calculate the actual s. Can you tell me how to calculate the actual s? Anybody?
So GP.
GP.
Yeah, simple GP. A upon 1 minus R. So that is 1 upon 3 by 2, 2 by 3. This is actual sum. And if you calculate the sum of first 8 term, which I marked in a green, so I'm just writing the direct expression for this. So this will come out to be 0.06640240625. This is a solved example, so I'm directly writing it from the book. Okay, you can check from various exercises as well. So now, if you think of s minus s8, is it positive or negative?
Positive.
Positive. Yeah. Why? Because your s is 0.6666 and so on. So here it is 0.664. Okay. So your s minus s8 is what?
Positive.
Positive. Okay. So that means you can also check it with a U9 as well. So what is your U9? Is it positive or negative?
Positive.
So your U9 is also positive. So that's what I was claiming, that if you take S difference of S and S state, it has the same sign as, not modulus actually. I shouldn't write the modulus in this part. Okay. So S minus S8 has the same sign as the U9, right? Can you see this?
Right, sir.
And now
Yes,
if you
sir.
take S minus S7, then it has the same sign with what?
S8.
S8.
U8.
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 Now your
U8.
U8 is negative. Your U8 is negative.
Yes,
Yes,
sir.
sir.
Yes,
So
sir.
same sign would be what? Negative.
Negative.
Yes, sir.
So we had few questions in our assignment that whether it is underestimating or it is overestimating. So
Yes, sir.
that part can be answered in this way. Okay. So if your S and Sn, okay, so you simply know that the difference of S and Sn, the sign of S and Sn can be estimated by Un plus 1. So if your Un plus 1 is positive, then is it underestimating or overestimating?
Overestimate.
Underestimating, na? See, if your Un plus 1 is positive, that means this is bigger and this is smaller. So this is lesser, right?
Yes,
So if it is lesser, that means it is not reaching to the complete sum. That means it is underestimating.
Yes, sir.
Yes,
And
sir.
if your Un plus 1 is negative, that means what? This is something like that. This is smaller. And this is something like that. This is bigger. That's why it comes out to be negative. Okay. So if it is negative, that means it is overestimating, right? It has a bigger sum. It is smaller. So it is what?
Overestimate.
Overestimating. Okay. So this underestimating and overestimating part can be solved, can be checked by looking at the UN plus 1. If your UN plus 1 is positive, then you say that it is underestimating. If your UN plus 1 is negative, then you say that it is overestimating. Okay. So that's it.